Today, we're going to dive deep into the world of engineering to uncover a hidden connection, a kind of secret language that links two fields you'd think have absolutely nothing in common. So, let's get into it.
So let's just start with a puzzle. What on earth could a car's suspension, all that metal and springs handling a bumpy road, possibly have in common with a stereo amplifier? I mean, one is all about heavy-duty motion, the other is about delicate electronics. They seem like they're from totally different universes, but as we're about to find out, they are surprisingly and deeply connected.
Okay, don't get bogged down by the details on these diagrams. Just take a look at the two different systems here. On the left, you've got a mechanical system. Masses, springs, just like our car suspension. On the right, an electrical circuit. The key to our whole puzzle is that both of these, even though they look completely different, can be described using the exact same mathematical language.
So, here's our roadmap for cracking this code. First, we'll explore this really unexpected analogy. Then, we'll meet the three key players that make it all work. After that, we'll actually model a simple system, then ramp it up to a more complex one. And finally, we'll see exactly why this power of translation is such a game changer for engineers.
So, how is this even possible? How can something that physically moves and something that flows with electricity be described in the same way? Well, the answer is in this really powerful engineering tool that lets us focus on a system's behavior, not its physical parts. And that tool is called a transfer function. Now, a simple way to think of it is like a mathematical nickname for a system. It doesn't care if you have springs or capacitors, it only cares about one thing. If you put a certain force or voltage in, what kind of motion or signal comes out? It's a beautifully simple ratio of output to input. It's like a cheat sheet for the system.
And listen, this isn't just some convenient trick. The source material is really clear that the parallel here is incredibly deep. The components themselves, the actual building blocks of these systems, have direct counterparts in the other world. And this is where that secret language really starts to open up.
Okay, so let's meet the key players that make this whole translation possible. To move between these two worlds, we need a guide. You can think of it like a Rosetta Stone that tells us exactly which mechanical part lines up with which electrical part. Now this right here, this table, this is our secret decoder ring. It's fascinating. A spring, which stores up potential energy when you stretch it, is basically the mechanical version of a capacitor, which stores energy in an electric field. A damper, think of a shock absorber that creates friction and burns off energy as heat. That's just like a resistor in a circuit. And a mass, which stores kinetic energy when it's moving, well, that's the direct equivalent of an electrical inductor. It's a one-to-one match.
So with that decoder ring in hand, we can come back to our transfer function. By using this analogy, engineers can turn a really complicated, messy, real-world mechanical problem into an electrical circuit problem, and those often have very well-known, straightforward solutions. It is a brilliant, brilliant shortcut.
All right, enough theory. Let's see how this actually works. We're going to take a simple physical object and translate it into a single, elegant equation that perfectly describes its motion.
The process engineers follow is really methodical and clear. First, you identify the physical system. Second, you draw a diagram to visualize all the forces involved, all the pushes and pulls. And third, you translate that picture into the language of math.
Here's our system. This is about as fundamental as it gets in mechanics. You've got a mass, it's hooked up to a wall by a spring, and a viscous damper. That's kind of like a piston moving through oil. We can push on it with a force, F of t, and what we want to know is how the mass moves, which we call its displacement, x of t.
The next step is to draw what's called a free body diagram, and this is an absolutely crucial step for engineers. You basically just isolate the object you care about, in this case our mass, and you draw arrows for every single force acting on it. So we've got our applied force pushing it to the right, and the spring and the damper pulling it back to the left. This simple visual map is what makes the math possible.
And boom! This is the final step, and it's brilliant. Using Newton's laws and a little bit of mathematical transformation, all those forces from our diagram get distilled down into this one single transfer function. This one little equation now holds everything we need to know about how this system is going to move. We've literally turned a physical object into pure math.
Okay, so that was a pretty simple case. But what happens when things get more complicated? Does our secret code still work? Well, let's find out. We're going to add another mass to the system and make it much more like a real-world machine. Here we go. Now we have two masses, connected by springs and dampers. This is starting to look a lot more like that car suspension we talked about at the beginning, right?
You could imagine one mass is the wheel and the other is the body of the car. Now, the motion of each mass starts to affect the other one.
And just like you'd expect, the math gets a bit more involved. Instead of one equation, we now have a system of two equations, because, well, we have to describe the motion of both masses. But look closely. The form of the equations is the same. The process of drawing a free body diagram for each mass and adding up the forces, it's identical. The method scales up perfectly.
So, we've seen this analogy in action. We can translate mechanical parts into electrical parts and physical systems into equations. But why does any of this matter so much? What is the real-world power of this secret code?
The benefits are just enormous. It lets engineers simplify incredibly complex mechanical problems. They can literally borrow decades of powerful analysis techniques from electrical engineering and apply them directly to things like robotics and suspension design. This means they can accurately predict how a system will behave, how a car is going to handle a bump, or how a robotic arm will move, long before they ever build a prototype. And that leads to better, safer, and more efficient designs in just about everything.
And here it is. This is the ultimate payoff. After practicing this translation enough, experienced engineers, they don't even need to go through all the steps anymore. They can just look at a complex mechanical system, like one with 3 masses, and write down the governing equations by inspection. They've become so fluent in this secret language that the translation is basically instantaneous. That is an incredible level of insight.
So this analogy, it does more than just help engineers solve problems. It reveals this fundamental hidden pattern in the universe, a language that connects the physical world of motion with the invisible world of electricity. And it really makes you wonder, doesn't it? What other secret codes, what other unexpected connections are just hiding there in plain sight, waiting for us to find the right way to look? Thanks for digging into this with me today.